Hello everyone, my name is Julia with Support Branches Tutoring, and today we're going to be talking about the universal law of gravitation, or also known as Newton's law of gravitation. So we have a problem here. It says the Earth orbits the Sun with a radius of 1.6 times 10 to the 11 meters. The Earth has a mass of 6 times 10 to the 24 kilograms and orbits the Sun in 3.2 times 10 to the 7 seconds. And part A says, what is the Earth's centripetal acceleration? Excuse me. So, first steps first, let's draw a diagram. It helps us kind of label things and figure out direction, particularly of different vectors. So we've got the Sun, and then we have the Earth, and the Earth is orbiting the Sun. And we know that they are separated by distance r, or the radius. And it gives us the radius as 1.6 times 10 to the 11 meters. And it gives us the mass of the Earth as 6 times 10 to the 24th kilograms. And then it says that the Earth orbits the Sun in 3.2 times 10 to the seconds. So that's kind of a change in time, or how long it takes to make one complete orbit. So it's 3.2 times 10 to the 7 seconds, and that's for one revolution or one orbit. And for part A, it asks us, what is the centripetal acceleration? So centripetal acceleration is the acceleration of the Earth that is causing it to move in a circular motion here. And we know centripetal acceleration equals the velocity squared divided by the radius. But we can also write this in terms of angular velocity. So angular velocity is how fast something is spinning, or how fast you can think of this Earth as going around the Sun. And the velocity equals the radius times the angular velocity. And so if we substitute that into our acceleration here, we're going to get our angular velocity squared. So these equations are equivalent. We can use either one depending on what we know. Now, we don't know anything about the velocity here, but we have some information that would help us solve for our angular velocity. And so this second equation here is going to be more appropriate in this particular circumstance. So let's go ahead and calculate our angular velocity here. So angular velocity is how much the angle changes in what amount of time. So if this Earth is making one complete revolution, that's basically one complete circle, you can think of that as 360 degrees. But we don't typically write angular velocity in degrees. We usually use radians. So 360 degrees is equivalent to 2 pi. So 2 pi radians is one complete circle. So that's basically our angle. It goes one revolution, or 2 pi radians, in this amount of time, which is 3.2 times 10 to the 7 seconds. So let's go ahead and put that in our calculator and solve for our angular velocity here. We're going to have 2 pi divided by the time, and make sure you put parentheses around your 3.2 times 10 to the 7. Otherwise, you're going to run into some problems. And we get 1.96 times 10 to the negative 7. And that would be radians per second. So if we kind of go over here, we're going to plug these in. We're going to solve for our centripetal acceleration. So we've got a radius of 1.6 times 10 to 11 meters. And then an angular velocity of 1.96 times 10 to the negative 7. And we need to square that. So let's go ahead and take our answer. We're going to take the 1.96 times 10 to the negative 7, and we're going to square that. And then we're going to multiply it by our radius, so 1.6 times 10 to the 11. And we get 6.2 times 10 to the negative 3, and that would be meters per second squared. Okay, so this is our centripetal acceleration right here. So that is our answer for part A. So let's take a look at part B here. So for part B, it says, what is the force of attraction between the Earth and the Sun? So this is really asking about the universal law of gravitation. And we know that the force between two masses, or the force of, we can think of it as force of gravity here, equals G, which is a constant, times the mass of object 1, or we could think of it as the sun, the mass of object 2, which we can think of as the Earth, divided by the distance or the radius between these two squared. And we know that G equals 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. Okay, so when we look at this, G is a constant, it's given. We know R, we know the mass of the Earth, but we do not know the mass of the sun. So we don't have enough information to be able to solve for our force of gravity. But when we think about force of gravity is pulling the Earth towards the sun, right? And by definition, that is essentially also what the centripetal force is, right? Centripetal force is a force that's pulling this Earth towards the center and causing it to orbit. And we know that the centripetal force equals the mass of the object, which would be the Earth in this case because it's what's orbiting, times the centripetal acceleration. And we just solved for AC, and we know the mass of the Earth. So again, the centripetal force equals the force of gravity here. And so even though we don't have the mass of the sun, we can still calculate Fg using our formula for centripetal force. So let's go ahead and do that. So the force of attraction here is going to be the mass of the Earth, 6 times 10 to the 24th kilograms, times our centripetal acceleration is 6.2 times 10 to the negative 3 meters per second squared. All right, so let's take our 6.2 times 10 to the negative 3, and we're going to multiply it by 6 times 10 to the 24, and we get 3.7 times 10 to the 22, and we'd have kilograms meters per second squared, which is the same as a Newton. And that is our answer for part B. That is the force of attraction between the Earth and the sun, or you can also think of that as basically the attractive force here, the force of gravity. Okay. Okay, so let's move over to part C. So part C said, what is the mass of the sun? So we just kind of said that the force of gravity equals the centripetal force here. And we calculated FC. We found that in FG was 3.7 times 10 to the 22 newtons. And we said that that was the force of attraction here. And we also know that that's equal to G, the mass of the sun, the mass of the Earth, over R squared. And good news is we know G, we know the mass of the Earth, we know the radius, and so we only have one known variable, and that's the mass of the sun, so we can solve for that. So let's just go ahead and plug in our numbers here. So we've got 3.7 times 10 to the 22 newtons equals G, which is 6.67 times 10 to the negative 11 newtons meters squared kilograms squared, times the mass of the Earth, which is right here, 6 times 10 to the 24th kilograms, times the mass of the sun, which is what we're looking for, divided by the radius, which is right here, 1.6 times 10 to the 11 meters. Don't forget the squared here. So all we gotta do is solve for the mass of the sun here. So we're gonna solve for that. The mass of the sun should equal 3.7 times 10 to the 22. We have to multiply by the radius squared. Put in newtons there. And then we're going to need to divide by G and divide by the mass of the Earth. Okay, so let's go ahead and solve this. So we have 3.7 times 10 to the 22 times 1.6 times 10 to the 11. And then we need to square that. Divided by, and watch your parentheses around this bottom. Times 6 times 10 to the 24. And we get 2.3. I'm going to go in and round it. 2.4 times 10 to the 30. And we should have kilograms here. Okay, so we've got the mass of the sun. And if we compare the mass of the sun here, it's larger than the mass of the Earth, which makes sense. We would expect the sun to have a larger mass. So let's go ahead and go over to part D. And part D is kind of a bonus question because it kind of goes beyond really this problem to talking about work and whatnot. And so it says, how much work is done by the gravitational force after the Earth has made half of its orbit? Okay, I'm going to draw the diagram again so we can kind of talk about this. So we have the sun and we have the Earth. And the Earth is orbiting here. And it says how much work is done by the gravitational force. So remember, our gravitational force would be pointed like this. Okay, and at any time point, it's going to be pointed towards the center. And it asks essentially half of the orbit. So if we start at time point here, half of the orbit would be time point 2 would be here. So what is work? Work is the force that is parallel to the distance traveled. And so we could calculate the distance traveled here. The distance traveled would be the length of this orbit. So again, if we started at time point 1 and we follow this path, this length here would be the distance traveled. And we often define that as arc length. And so it's the radius times the change in our angle here. And so for half a circle, that would be 180 degrees, which is also equivalent to pi radians. And if for this r times the change in the angle, it has to be in radians, otherwise we have to like convert it to radians. So here we could calculate the distance traveled as being 1.6 times 10 to the 11 meters, because that's our radius, times pi. And that would give us our distance in meters. So 1.6 times 10 to the 11 times pi. And that's 5.0 times 10 to 11 meters. Okay? So the Earth has traveled 5 times 10 to 11 meters when it goes from point A to half of its orbit, point 2. Okay? So that's distance. That's D. What about force here? Well, let's take a look at the Earth kind of say at time point 1. At time point 1, it has the force of gravity that's pulling it. You can also sense that's the centripetal force here. And then it's got a velocity that would be 90 degrees to that. And then it's got you can kind of think of the angular velocity is the curved, would be here. And so, well, what is our d? Well, our distance here is really pointed in the direction here. Okay, so if we look at this, we have our angular velocity or velocity and our force. And the question asks, how much does the gravitational force, how much work does it do? So we're talking about this force here that's pointed towards the sun. And so this distance that we calculated, the 5 times 10 to the 11 meters, you can think of it as being kind of the same displacement or direction of the velocity. Because as the Earth moves here, again, our force of gravity is going to look like that. Our displacement is going to look like that. So they're always going to be 90 degrees. And so anytime the force and the displacement are 90 degrees, you have a cosine of 90 degrees, which is 0, then your work is 0. So even though the Earth had a displacement, it had d, we calculated that, it was 5 times 10 to 11. Since that displacement is 90 degrees to this kind of attractive force, we have no work done. So no work is done by the gravitational force as the Earth orbits the sun. And that's one of the reasons this is kind of listed as a bonus question, is because it's a little bit of a trick question. But good to go through. So I'm gonna leave you with this. This is from Luke 6:27 through 31. It says, "But to you who are listening, I say, love your enemies, do good to those who curse you, pray for those who mistreat you. If someone slaps you on the cheek, turn to them the other also. If someone takes your coat, do not withhold your shirt from them. Give to everyone who asks you, and if anyone takes what belongs to you, do not demand it back. Do to others as you would have them do to you." And that's Luke 6:27 through 31. Very high order. We don't like to love our enemies. We don't like to do good to those who mistreat us. But God has perfect wisdom, and so it's something that we can take to heart. So God bless, and never forget, Jesus loves you.